Welcome back. So let's continue with our URANS tutorial. So we already addressed this one, no sources. Okay, so we're happy. So now let's move to this one, K-Omega SAS Scalable Adaptive Simulation. We already addressed the theory, and I hope you already draw this conclusion that if you would like to capture unsteadiness, vortex breakup, and so on, this likely is the best model within the RANS category. So let's move to this case. Remember, all the other cases we have exactly the same models with the also forcing enable, and later in another video we're going to compare. Okay, no need to run everything. We have the video, so I'm going just to enter here some comments and well, probably run everything. So we have high re, low re. I'm going to enter to high re. Remember, boundary conditions exactly the same. We already talked about also in the previous video that you can add the fluctuation here. You have this option. So there are many ways to add that tripping. Okay, we're working in this case with the numerical tripping forcing. So you can add boundary conditions. It can be in the geometry, adding sources and so on. In our case, that what we're doing is this volumetric sourcer that we add somewhere in the domain to trigger that effect. So this is exactly the same new option. Okay, so this is the one I'm using. I find it very easy to implement. There are many ways to do it. The one you can also play around with the different options. You have access to a specific values, velocity, and so on. Okay, so you're going to use this one that gives me all the behavior that you have seen so far knowing the animations. And now we go also system, and in system, okay, we have this. Okay, let me go here. Nothing changed. Okay, remember everything exactly the same. Very important, SB skin, choose your numerical discretization, SB solution also. You have it there, you're looping here for the pimple loop. On the relaxation, I always recommend to put there 0.9, and that's it. Okay, remember that some methods use the wall the distance from the wall, so this K-Omega SAS use, so be careful about that. And I always recommend to use the mesh wave. So in control did everything exactly the same. On steady, I always recommend compute a statistic, because at the end of the day you are interested in looking at statistics, not instantaneous values. Okay, the instantaneous values pretty much will be to do those eye-catching animations. For taking no critical decisions, this is what you are looking at, statistics. And very important, and also we saw in the video how to control your time step here in this simulation. So you have two options that you can use a just a time step, yes, and then fix your current number. In my experience, I would say up to 5. You are not adding too much numerical dissipation. We studied that. More than that, it is going to be something that the simulation is going to feel. You're going to add diffusion there and maybe underpredict, overpredict the results. Who knows? So be careful about this. We're going to run in this case with 4, which is marginal there in that limit, but you can go to 1 for better accuracy. So that's how you do is you want to enable this one. If you don't want to use this one, you can go for delta T and you change it here. So you can change this dynamically. So it's up to you. I will say that pretty much this is okay, but there are some situations that using this one is not okay, because this is dynamically changing. Okay, so for iteration 1 to 2, the time step will change just to keep the current to 4. And those changes in time step can add some oscillations in your solution, instabilities in your solution, so it's better to fix it. So usually DNS less will suffer of that. Also multi-phase simulation. So to mention something at this point, we're done. We have covered everything, and what I'm going to do here, run all, and off you go. We have the simulation, everything perfect, and now we need to wait for the results. And also let me put here Anaconda 3, Anaconda 2, and Python plot washer log solver, and let me put everything that we have there with all. So all the monitors, so iteration, so we're putting a lot of information. Look at the current number and how it's changing. This one, your residuals, delta T, continuity errors, and I think these are bounded variables. So you have some unboundedness for K, but nothing to be worried, it's just very well contained in that value. Okay, so at this point, whoops, go down there, minimize, put it there, residuals. I think pretty much we're ready. Okay, we need to wait. So this will run, and I don't recall, I think up to a time of 100, okay? But what is very important here, so look at that, we're running, 100. We're running the high rate case, the wall function. So here you have that in this case is 60, so we're in that sweet spot, it's a nice value. And look at that, for this y plus of 60, we have this time step that match this current number. For the other case, the low rate, that the y plus is about 1, I don't recall, 0.5, as the distance from the wall to the first cell center is very small, okay, your time step will be much smaller to match this current. So here, instead of having 003, you will have 0.00005, I don't recall, but it will be very, very small. And to stress this is the advantage of using wall functions, okay, that it will let you use a slightly higher time step, and at the same time keeping the same accuracy. Coming back to URANS, also the advantage of using URANS RANs instead of less, because now also you will have the meshing requirements close to the wall are much larger. Okay, you need to think about X set plus, only Y plus, and you can put wall functions and things can advance fast. And we have seen that if you follow a good standard practice, you're going to get good results. So pretty much running. I think I don't need to do anything. I will let it run in here. What I'm missing, we have everything, and yeah. At this point, let's wait for the results, do some post-processing standard, and we can close this chapter with the SAS model and talk about the other models. So let's wait for the final result. Okay, so we're back. So after a long simulation, we have a result. So here it took this time. You have everything here, all your monitors, nothing strange. Remember, what you see here is just reflection of the unsteadiness, initial residuals, not a problem. Everything seems okay. Your CFL number, no. Look at how it's oscillating a lot. And as I mentioned, this oscillation from let's say 2 to 4, that it can introduce some problems in less DNA, some multiphase. So that can lead to maybe divergence. So in those situations, it's better to have a fixed time step. So let me close this. We have the solution, we move here. So now it's doing some other post-processing there. And what I would like to take a look here, it is that I already have a log file here now of the low rate. And let me go here. What I was saying that for the same CFL number, your delta T tends to be smaller in a wall resolving mesh. Okay, so let me go here, 002. So since that probably they are a little bit similar, okay, 004. So they're here. So we will need to go here and let's go till minus 100 got solver. And in this case, look at that, we have a delta T 003, 004, okay? And that it is just 001 different, but it can make a difference when you are running. The advantage of using a wall resolving meshes. So at this point, we have a solution. The big question now is, but how long do I need to run the simulation? Because I run here 100 seconds, probably too much, okay? So, and that is the importance of the statistics. So usually it is up to you. You will say I will run 110, 100, 1,000, it's up to you. Okay, but time is a very valuable commodity, and not everybody has infinite times or limited time. So we need to set a limit there. And basically, everything depends on statistics. So if your solution from a statistical point of view, it is steady, statistically steady, you can say you can stop the simulation at that point because your statistics are not changing in time anymore. Okay, so how do you know that? You need to monitor the solution, put a lot of probes, look at the velocity oscillations, forces. If you have forces, we'll look at the previous video, know the case. Okay, that we can get that idea by looking at the forces or plotting results and so on. So there are many ways, but it is tricky. Post-processing on steady simulations is something tricky. So for instance, if you want to look at this one, you can look at the mean value. So look at that from the beginning, and it keeps running. The mean value, it is changing. So I cannot say that, okay, you can stop your simulation here. You need to let it evolve, okay? And when you reach a point that this mean solution is not changing anymore, it might be the case that, okay, I can stop my simulation here. It is, from a statistical point of view, it is something steady, okay? So there are many things to do here in the post-processing. I don't want to get lost here, but there's a lot to cover. So just to show you, let me go ParaView again. You have your scripts here. Let me open this one. And we're going to load all the times. So remember, we have time dimension here. So for instance, talking about how do I know that I can stop my simulation? And let me play here and look at that. You have the evolution. Now you have time. Where do I have time? I have it here. So basically, when you start to see that the solution is not changing anymore in one quantity. So in this case specifically, we can take a look at the friction coefficient. So look at that, it's changing a lot. So the point when those changes are not significant, that's the point that you can say you can stop your simulation. Then also remember that you have instantaneous quantity, you have the mean quantity from OpenFOAM, and you can get your fluctuating quantity, which will be U minus the mean quantity. Get the fluctuating quantity. With that, you can do a lot. You can compute Reynolds stresses. So later, when we talk about that model, I'll show you that. We also did it for a steady case. So pretty much this is it, okay? And let's take a look here at the high resolution that we have it before ending this video. And then we discuss the other cases by just looking at the solution. And let me open this here. So low res, high res. We move it here. Let me put it here. We put it here. So wall function, wall resolving, and exactly the results that we were expecting. So look at here. So everything we're looking at time 100. Okay, so you have this behavior here. So obviously this might be a better resolution because we have a better mesh here in terms of white plus. We haven't studied the other directions. Okay, and let's move to the other one. Okay, we already studied all this stuff in URANS. No need to recover that. So to re-study, revisit that, and we move to the other one. Okay, always the last time since time 100, and look at that. Everything makes sense according to the theory that we have studied, and clearly here you can see that on steadiness. Okay, and let's move to the next one here. And there you go. So in this case, we have this fluctuation. And interesting that here we're plotting U prime. U prime, okay, will be instantaneous minus U mean. So this is the fluctuation that you see plotting there. So if I move the next one, here we go. Yeah, we have the movies. And this is it. Wall modeling, wall resolving. Remember when plotting in ParaView to choose the right wall shear stresses. So here everything is done in reference with the last times. But this is it, a truly on a steady simulation. This is the stuff that many times you cannot see in URANS, and will be very interesting because when we look at the URANS, you will see that some URANS models, it will completely smear the solution. You are not going to see that, and that is due to the modeling effect. Okay, so that's very, very interesting. So there you go. So this is how you run an URANS simulation. In this case, we had to force this unsteady behavior because due to the averaging, everything is remove all the fluctuations. In some other cases, no, like the cylinder or a square or circular, you can get that, but you are not going to get that vortex breakdown that people likes to see. So that's all for this case. So the K-Omega SST-SAS. Let's move and discuss all the other cases that we have here now with the tutorials that you have the link now in your video description. So see you next time. Bye.